Okay.
Yes. Thank you so much for that introduction. My name is Marcella Hastings, and this is an SoK paper, so I'm going to be talking about the results of our survey. So the tool we were looking at was secure multi-party computation. This is a cryptographic tool that allows a group of mutually distrustful parties to compute an arbitrary function on their joint inputs without revealing anything beyond the output of the computation. So the most famous example of this in practice is the Danish beet auction. In this setting, we have sellers, who are Danish beet farmers, and a single buyer, the only beet processing facility in Denmark. The sellers have prices at which they're willing to sell their beets, and the buyer wants to find a market clearing price. But the sellers might not want to reveal their bids because it could reveal information about their businesses and their farms, especially over several years. So they use secure multi-party computation to find an appropriate market clearing price without revealing the value of their bids. Another example is a collaboration with the Boston Women's Workforce Council, which is studying the gender and racial wage gap. Companies might not wish to reveal or might be legally prevented from revealing financial information about their employees. But by using secure multi-party computation, they're able to compute the relevant statistics and analytics without giving up that data. Now, all of this is to say that secure multi-party computation is a tool that's efficient and practical enough to be used in real situations. However, many of the practical examples we've seen in the past have required a team of cryptographers to implement a special purpose MPC engine for that specific use case. And if we want to see MPC have more widespread adoption, we need tools that are usable by the layperson. So although algorithms for MPC have been around since the 1980s, they were assumed to be too inefficient for practical use until the Fairplay compiler was presented in 2004. This was the first general purpose framework which could take an arbitrary function and execute MPC on it, and it started the beginning of a huge and fruitful field. Performance improvements over the next decades rapidly advanced the state of the art, both algorithmic and in the implementations. And the number of end-to-end frameworks exploded in the past decade. So in this work, we're looking at general purpose end-to-end frameworks. And so end-to-end frameworks look something like this. They have two phases, a compiler and a runtime. This is because most MPC algorithms operate on only a limited set of primitives, like addition and multiplication mod prime. And it's hard for a developer to reason about interesting computations using that very limited model. So we looked for frameworks that have a compiler, which takes a function description in a high-level language and converts it into a representation that can be executed by the algorithm. Then the runtime phase is the actual execution of the protocol. It is run simultaneously by multiple parties, and who each take the output of the compiler and the private inputs of each party and compute the function output. And of course, the architecture varies a lot based on different frameworks, but they're all taking this general shape. So in this survey, we wanted to ask some questions about where we are, where the frameworks are. You know, who can use them? Are they ready for real computations? Can they express interesting functions? You know, can they be used for real situations? In order to answer these questions, we surveyed 9 frameworks, end-to-end frameworks, and 2 circuit-only compilers. We recorded different features of them based on the protocol that they implement, the data types and operations that they support, and other details of the implementations, and we evaluated them on a variety of usability criteria. In order to collect all this data, we implemented 3 sample programs in every framework. So we collected our sample programs plus complete build environments for every framework that we used and put them into an open source framework repository. This also has additional documentation based on our experiences using the framework. We estimate this repository took about 750 person hours to produce. And it is open source, and we're actively maintaining it. So I encourage anyone to check it out. Now I'd like to talk a little bit about what we found after doing all this work. Overall, most frameworks are in good shape. We have a diverse set of threat models and protocols that they implement, so depending on your use case, there are different options. We were able to implement our sample programs in almost every framework. which means that the high-level languages are expressive for many situations. And overall, most of them were open source and compilable and usable. However, we did find two major areas for improvement. One is that there were significant engineering limitations, for example, complicated build systems, and the other is significant barriers to usability, which are mostly rooted in a lack of documentation. So before I go into those issues, I'd like to give you a higher level picture of what we found. So these are the 9 frameworks we looked at, and the 2 circuit compilers at the bottom. You can see the number of parties they support and the threat model. We have 2 threat models here in the semi-honest model. An adversary is going to execute the protocol correctly, but will try to learn something about other parties' input. In the malicious model, the adversary may not stick to the protocol and will try to induce an incorrect output. We also created a loose taxonomy of 3 different protocol families, which I'm going to talk a little bit about. The first is garbled circuit protocols. These were first introduced in the 1980s by Andrew Yao and have been essentially continuously developed since then. While theorists have produced a wide variety of settings in the garbled circuit model, we found in practice that they're almost all implemented as semi-honest 2-party protocols, where one party garbles or encrypts the circuit and sends it to the other party who evaluates it based on their input. And these typically represent functions using Boolean circuits. The second type encompasses a wide variety of protocols, which we call multi-party circuit-based protocols. Now, these are protocols that have 2 things in common. The first is that they represent functions using a circuit, either arithmetic or Boolean. And the second is that data is represented as linear secret shares. So the linear secret sharing means that these protocols can typically support an arbitrary number of parties, where the parties work together going gate by gate through the circuit to convert secret shares of the inputs to secret shares of the outputs. However, within this model, the way that they do this conversion can be executed in different ways, maybe information theoretic or cryptographically secure models. Now, we expected these 2 protocol families to cover the majority of implementations. However, so in theory, most theoreticians define MPC protocols, again, on a very limited set of functions, of operations, either addition and multiplication, mod and integer, or bitwise and XOR. However, in practice, and these are universal representations, so you can express any function using that. However, in practice, you can often define optimized subprotocols for common functions that you have, like division or comparison in an arithmetic model, that are more efficient than reducing all the way to these very low-level primitives. So we found 3 protocols that implement certain subprotocols, and we call these hybrid protocols. And then at the bottom, you can see our 2 circuit compilers. Now, one major thing that people need to consider when they're choosing an appropriate framework for their use case is the level of abstraction of the high-level language. So we saw a variety of these, and I want to walk through a couple of them. The example we're going to use is one of our sample programs, which is the inner product. It takes the sum of the pairwise product of 2 vectors. So Frigate is a circuit compiler, and it uses a pretty traditional C-style abstraction. And you can see an implementation of the inner product here. You take a result, and then you loop over your vectors. For each element in your vector, you multiply them together and add them to your sum. Now, this is pretty straightforward and makes a lot of sense. However, if you're familiar with MPC, you might recognize that in a linear secret sharing-based model, you can parallelize all the multiplications into a single round of communication. So if you want to have that optimization, then you might use something like Pico. Pico recognized that you can do this optimized multiplication step, and so they implement a custom primitive, this is one of our hybrid languages, for the inner product operation. And you can see you just use this very simple infix, custom infix operator to execute an inner product on any size vectors. Now, this is really good if you're not super familiar with the cryptography and you don't really care what's happening under the hood. However, if you are a cryptographer and you're working on perhaps a more complicated function than the inner product, you might want to have more control over exactly the circuit that you're going to have produced. In that case, you might prefer a framework like ABY. ABY is implemented as an end-to-end framework. It's implemented as a library in C. So you can see we have a share type that holds our private data. We put a multiplication gate in, and ABY does implement these parallelized multiplications. So you need a single multiplication gate to do pairwise multiplication across your whole vectors. And then you sort of break apart your vector representation to add up the individual elements. Now, this gives you a lot more freedom to do exactly the thing that you want to do, but if you have less cryptographic familiarity, you might not want this much power. So that's sort of the range of front-end high-level languages that we saw. The next thing I want to talk about is some of the limitations. As I mentioned, software engineering was a major issue. You have to keep in mind that most of these frameworks were developed in academic settings and are therefore subject to the engineering constraints of such a setting. So keep that in mind as I go through the next couple things. One major pain point was the build systems, which tended to be extremely complicated. You often had to compile a specific OpenSSL version from source, which takes a long time, or set up a custom certificate authority to ensure private channels in your communication. On average, it took us 1 to 2 weeks just to compile the existing frameworks. This is very frustrating, but luckily for everyone else, we put this all in our Docker repository, so no one should ever have to do this again. Beyond these build systems, though, these are significant software projects that require a lot of software development. In addition to implementing cryptographic protocols, which is notoriously difficult to do correctly, programmers have to implement a variety of supporting systems, like distributed communication and interfacing with other systems that, other communication systems and insecure languages. This results in just small but frustrating things. For example, in Oblivion, we weren't able to write a computation that returned more than 32 bits. This is a problem that could be solved with more hands-on keyboards and some time, but given the constraints of the academic setting, not all the frameworks have these kinds of engineering perfection. The other major issue we saw was in usability, and especially in documentation. We defined 5 types of documentation, which you can see here. Half the frameworks had no more than 3 of these. I'm not going to go through all these different types in detail, but I do want to give you a few examples of places where there were limited language documentation that made it more difficult to use the frameworks. And language documentation is anything that describes how the high-level language works. So CBMC GC is a circuit compiler that compiles a subset of ANSI C. So most people are familiar with C, and you'd assume that a simple program like this, which multiplies 2 numbers together, would just work. However, we get an error that says, did you forget to return a value? It turns out that in CBMC GC, all private inputs to the computation have to have variable names that start with input. And this isn't an issue, but it wasn't written down, so we had to sort of figure it out. Another example is from Oblivion. Again, this is an end-to-end framework that consumes a Java-like language. And again, we have our program to multiply 2 numbers together, and it encounters a parsing error. It turns out that Alice and Bob are reserved keywords in the language, and so you can't use them as variable names. Wisteria is an end-to-end framework that was developed by programming languages people, and so it uses a novel functional representation. And they include an extensive language guide for people who might not be as familiar with that functional style. However, the language docs, this tutorial doesn't account for the limitations in the parser, so a developer has to put a lot more parentheses in than the tutorial would imply. And then EMP Toolkit is a framework we really liked using. It's a garbled circuit-based framework. However, we found on average 1 comment per 600 lines of code with no additional documentation in separate places. So these are all things that make it more difficult to use these frameworks. However, there were some frameworks that did a really good job with documentation. I'd just like to thank them here. We do have 2 major takeaways for anyone who maintains a large open source project like this. First is that having multiple types of documentation, even if it's mediocre, can drastically increase the usability of your framework. This could be something like one document that explains the architecture of your framework, and then a commented example file that demonstrates some features of your high-level language. The other thing we recommend is an online resource, for example, a mailing list or a GitHub issue tracker. These are a super sustainable way to produce documentation for your framework. It creates a living FAQ so you don't have to repeatedly answer questions via private email. And it also allows a place for users to interact so they can answer each other's questions. And if you end up not maintaining your framework, users can still talk to each other and find solutions to their issues. So, looking forward, even given these engineering and usability challenges, MPC is in pretty good shape. We were able to implement lots of example programs, and overall things look pretty good. These usability challenges are acknowledged by the community. The IARPA Hector program is funding the next generation of MPC frameworks, and they have specific usability criteria included in the grant. We do recommend that future developers consider working with programming languages researchers. Most of these frameworks were developed by cryptographers, and therefore the front-end languages are perhaps not as principled as they might be if somebody with extensive compiler experience helped develop them. And then one last plug, our repository is actively maintained, and we're accepting pull requests from new and existing frameworks. If you maintain one of these or would like to use this as a starting point for your academic project, we encourage you to check it out. And then one last plug, I am looking for projects related to MPC in practice, so if you are a potential collaborator and you have an interesting project, please come talk to me later. Thank you.
Very much. Any questions? Please come to the microphone.
Hello. First, thank you very much for all this. This was very much needed for the community, and I think it's a very amazing work. So I know that you did all these great compendium of things, and then you got the good things and the bad things of each, but you didn't really give a sort of this is the framework, this is the one we say the community should continue building on top of this one or something like that. And I think it's important if you have some word on that, because if not, what people end up doing is oh no, there are 12 standards, let's try to standardize this, and of course you end up with 13, right?
Sure.
So do you have a word on that?
Sure. So in the paper, we do give stronger recommendations as to which frameworks we recommend. If you're looking for a specific recommendation for a setting, there are sort of 4 that I would say stand out above the rest. For garbled circuit frameworks, obliv-C is a good general purpose framework, and EMP Toolkit is really good if you have a little more cryptographic expertise. And then Scale Mamba is sort of the best of the multi-party, or it's actually a hybrid protocol, so it's sort of the best of these linear secret sharing based protocols. It's really extensive and it's actively being developed. And then if you are a person who has actual security needs, you might be interested in ShareMind. This is the only framework that has paid developers working on it who aren't academics. So those would be the sort of strong recommendations I have.
Thank you.
So I'm actually absolutely going to develop a programming language in which Alice and Bob are reserved words. That's cool.
Great.
Okay, thank you very much again.
Thank you.